Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello. Hello, everyone, and thank you for joining our webinar session today for the 2023 AI ML in 5G Challenge. My name is Mia Nishio with ITU, the International Telecommunication Union, the United Nations Specialized Agency for Information and Communication Technologies. The Machine Learning in 5G Challenge, now in its fourth year, aims to create a community to solve network-related problems using machine learning. For returning participants to the challenge, please be aware that this year we will be running problem statements all year long, with each having their own respective deadline, unlike in the previous years where we had only one overall deadline. The registration for today's specific problem statement starts today and ends on the 31st of August 2023, with submission deadline being 8th of September, which will be followed by evaluation in October. The challenge this year will be featuring a batch of new problem statements, all relevant to the updates and progresses we've seen in both AI and communication networks. The title of today's session is Multi-Environment Automotive QoS Prediction Using AI and ML. We are counting on you, the participants, to help create an engaging discussion. So if you have any questions, please type them in the video wall and we will take them during the Q&A session. Without further ado, I would like to introduce today's first speaker, Rodrigo. He is currently working towards his PhD as a research associate in Berlin, Germany, and his interests include application of machine learning and signal processing to wireless communication systems and radar, as well as the integration of both radio technologies. Over to you, Rodrigo.
Oh, thank you very much for the nice presentation, Mia. So yeah, as you've said, I'm working at the Fraunhofer Heinrich Hertz Institute on communication and sensing, and we apply machine learning for different problems. So that's, I guess, the starting point of the challenge, that the problem statement that I will present today. So let me just start sharing my screen, and maybe you can shortly confirm that you can view it.
Yes, we can see your screen.
Okay, perfect. So as you've mentioned, the name of the problem statement is Multi-Environment Automotive QoS Prediction Using AI ML. And sorry, I'm just going to minimize. Okay, now I can see the full screen. So yeah, and I guess the best way to introduce the challenge is by letting you know the research project where it all started. So rather than just introducing my research institute in detail, I will tell you about AI for Mobile, which is a research project funded by the German Ministry of Education, where different institutions from industry and academia came together for 3 years to research on AI and ML for predictive quality of service at high mobility in wireless networks. So when we speak about high mobility, in the scope of this project, we had two main definitions of it, like two application areas. One was traffic, so basically connected cars that used mobile network to exchange information. And also in industry, so this would apply mainly to automated guided vehicles or moving robots that move in an industrial site to fulfill one task. So today's challenge is constrained to the first definition, to the traffic area, application area, and so these highlighted companies are the ones that contributed to the measurements, to the data preprocessing and the analysis of the data for this challenge. So you can see that we have some important companies like BMW and Ericsson, as well as research institutions, namely like my institute, the Fraunhofer Heinrich Hertz Institute for Telecommunications, based in Berlin, as well as the universities of Kaiserslautern and Dresden. And the latter one even had 2 chairs in place for Deutsche Telekom and Vodafone, respectively. So if you want to know more about this research project, you can also visit our website. So as I've just mentioned, our goal was to research on AI and machine learning for predictive quality of service. And as you may know, to test machine learning algorithms, we need data. And there has been a lot of efforts in recent years to capture data, wireless data that can help us to build machine learning algorithms. But for these application areas of high mobility, we felt that we needed to go out on the field and measure more data that fits our research interests. So that's where it all started. That's why we collected some measurements, and most of them we published them online to be able to investigate machine learning in the context of quality of service prediction. And as I've just mentioned, we are not only restricted to automotive areas, but we also have some data sets on the industrial side. Although for today, I will just focus on this first dataset that is publicly available. As I've said, this Berlin Vehicle to Everything dataset, or Berlin V2X for short. So now that that's clear, I will start with the proper presentation. So first, I will give you a motivation why we are interested in multi-environment automotive quality of service prediction and what the challenges are. Then I will go through the data set to the best of my ability, and I will end up introducing the problem statement so that all participants who feel like investigating the data can get their hands onto it. So our motivation for quality of service prediction in the automotive area comes from the fact that vehicle to everything communication, it's at the core of new car services. You can think of autonomous cars, or like just some cooperative service between vehicles on the highway. So there will be some information exchange. And at the beginning of our research project, we actually identified these use cases. And yeah, I mean, I'm not going to go through the details of these graphs here, but I just want to mention that most of them come with a quite strict quality of service requirements. But interestingly enough, this notion of quality of service is not unique. So depending on the service or the use case that you are considering, maybe throughput is interesting for you to provide quality of service or low latency. So this calls for a very holistic approach when measuring data. Machine learning is all around in communication networks for different activities. So we also want to leverage the boom that this machine learning community has given to our research area. So the problem is if we are going to consider communication scenario in between cars that are moving on a highway, this leads to a radio environment that's continuously changing. And this doesn't fit quite well with the typical setup of machine learning, where you want your training data and your testing data to be as similar as possible. So you have data distribution drifts, which means that the samples that you get are no more independent, are identically distributed. And this leads to problems, to generalization problems when you consider data from different radar environments and also different entities. If you train with one vehicle and test on a different one with a different operator, so all these different categories need to be taken into account. And I just put here a couple of graphs extracted from our data that exemplify this. So the kind of data rate distribution that we get on an avenue environment for one operator is quite different as the one that we get in the highway for a different operator. And you can also plot a correlation matrix and calculate these cross-correlation entities between operator 1 and operator 2, and you will find this as well. So it's important to take a multi-environment approach in this regard, and this is why we when we devised a measurement campaign that incorporates different environments so that we can play around with these different categories. So basically we performed LTE measurements from two commercial mobile networks, Deutsche Telekom and Vodafone, in the frequency bands of 700 to 2700 megahertz. This would be the vehicle to infrastructure part of the data, but we also perform some vehicle-to-vehicle measurements with this sidelink from 3GPP release 14. I just want to mention this because the name of the dataset is Berlin V2X, vehicle to everything. So we have communication to the infrastructure, to the base station, and also directly between vehicles. But this is not going to be part of the challenge. It's out of the scope. I just wanted to mention because the measurements are also there bundled together with the LTE measurements, and maybe for some other application it will be interesting to take that into account. But I'm going to just focus on the LTE measurements today. So we performed these measurements with up to 4 vehicles that were driving in West Berlin at the same time, and we just assigned 2 vehicles to one operator and the other 2 to the other one. And we also played around with different modes of driving. So we were driving together in a platoon, or we drove also in pairs of 2. And we also played around with the throughput profiles that we were using to communicate over the mobile network. This will become clear in the next slides. Just to being able to measure different QoS parameters. The point of telling you all of these different small parameters is that we combine them in 17 rounds over 3 days to be able to capture all these different nuances and combinations in the data. And this, when I say round, this was a predefined route of 17 kilometers in West Berlin across different urban areas that took us like 45 to 60 minutes on average. Here you have a clear idea of how this route looks like. So this is a map of West Berlin, and we designed the route in a way that we drove along an urban highway. So we have like, we could drive in at higher speeds here, but then we also drove on an avenue, like 4 lanes per direction. And also in the park, which is basically the same environment as avenue, but it provided us with some cool photos with the Brandenburger Gate in the background, and also to vary and have more of an urban radio environment with smaller streets, narrower streets, and tall buildings. So we also drove through this residential neighborhood of Wilmersdorf, where we had this kind of urban canyon setups with like these buildings close together. And also, I forgot to mention that in the highway there was a small portion of a tunnel where posed us some problems in terms of connectivity loss. And you actually can see from this map that we plotted heat map of the signal to noise ratio on top of it, and this already captures in a way this the variety of the measurements along the route. So what did we measure actually? And how did we do it? Which tools did we use? So for the LTE measurements, we just used this tool called Mobile Insight to capture all the LTE information from all the LTE stack that it's available at the vehicle side. We were using some in-vehicle devices for this. And we were able to do this because we were continuously exchanging traffic and information with a server at our institute. And while doing so, we were also measuring data rate and jitter with iPerf, and as well as the latency via ping-based delay. And here, I think it's a good point to recall this idea of measuring of different throughput profiles. So what I meant by this is that depending on which what's your notion is of quality of service, you need to exchange traffic at a different rate to be able to tell how good your network is in those terms. So if you want to measure what the possible best latency is that you can get through the network, you need to exchange messages at a low throughput because otherwise the size of the messages will interfere with the minimum delay that you can achieve. On the other hand, if you want to be able to tell how much throughput your network can hold at a given moment, then of course you need to send with a high throughput as much as you can. So, and this of course depends whether you are doing it in the uplink or downlink because of the asymmetry of mobile networks. So this in the end leads to these figures here that for the low throughput we were exchanging 400 kbits per second, and we had this like 700 mbits and 75 mbits and 350 mbits for the data rate measurements. Of course, we were driving around, so we also had GPS measurements to be able to pinpoint the position of the cars, and we also included some site information on weather and traffic via APIs. So this is also this data that I just commented that we measured in a tabular format. And what I want to comment based on this table are three things. One of this is that all these different measurements don't necessarily have the same sampling interval. So for the LTE, we had a very high granularity, but the quality of service we were doing it at a second based on like a 1 second interval. So in the end, we needed to put all these different sampling intervals on a common value. Also, Mobile Insight is a very powerful tool to do LTE measurements, and it gives you a lot of messages with different types of information. So we pre-processed basically three different types of information with different sampling that came at different sampling rates. Things like signal quality and signal measurement, signal quality and signal strength measurements, also information from the physical downlink and uplink shared channels on the number of allocated resource blocks, the transport block size, and in the downlink, the modulation and coding scheme and the transmit power for the uplink. And also some information on the cell identity. So which cell is the data coming from, and what's its frequency and its bandwidth. And the third thing I want to stress is that because we have all these different measurement parameters like our target data rate, our operator, and so on and so forth, we also included all these metadata in the pre-processed data. So we have both pre-processed data and raw measurements available online in this IEEE Dataport platform. It's all saved as Parquet files, and so you can really access all these high granularity measurements. However, maybe you may start to think that this is quite a complex measurement infrastructure or measurement setup. So in order to bring everything to a very easy data set that it's easy to work with, we pre-processed all these data sources that I just had in the previous slide. And we also uploaded it as this cellular data frame.parquet file. And basically the pre-processing steps is bringing everything down, all the data to a sampling interval of 1 second, extracting these LTE messages that I mentioned in the last slide, merging everything together. Also, an important thing to add here is that due to this carrier aggregation phenomenon in LTE cells, at a given point in time, one device might be served by several cells at the same time. So, so all these 3 types of information that I presented in the last slide, it's actually double, because you have, I don't know, signal quality measurements from the primary cell, but also from a secondary cell at the same time. So these values for primary and secondary cells are included as separate columns. And yeah, and once you have all these very detailed pre-processing on the LTE information, we just merged it together with the other data sources and put the label, and we uploaded it here, and it's open access for you to work with it. So this is just an excerpt of how this pre-processed data frame looks like. So the rows are indexed by timestamp and device. So PC4 to PC1, the vehicles 4 to 1. And here, these columns, these are an example of the LTE measurements on signal quality and cell identity. You see that you have one column for received signal strength indicator from the P cell, from the primary cell, and at the same time from the secondary cell. It's not always the case that one device is connected to primary and secondary cells, so you may have not a number or some missing data. What else do we have? We have QoS measurements, the GPS, temperature, traffic, and the metadata. Also, an interesting thing to comment here is that here you can see the effect of the different throughput profiles that I mentioned before. So if you take PC4 at this time, we were measuring data rate. So we were exchanging traffic at a data rate of 350 megabits per second. But for PC3, we were measuring delay. So we had a target data rate of 400K. And you can see that the achieved data rate in this column, it follows the target data rate. It actually exceeds it a little bit. But in the case of this big data rate, it comes at the cost of having a very large delay. So this is a justification of the different throughput profiles. I think this is, there is much more to say about the data, but I think this is enough for the purpose of the challenge. And I just want to also give you these resources here. Again, like the data is available, open access in IEEE Dataport, the code, more specifically the code for the pre-processing, it's in GitHub. Both these IEEE Dataport and GitHub sources are documented in a lot of detail. So what I just said now, it's also explained there. And for a more academic analysis, we wrote a paper that it's available on Archive. Also introduced, explaining the measurement campaign and all these details, but we also gave some ideas which kind of ML studies might be interesting, and a first analysis on the data to give a clue in which direction to investigate. And it's available already on Archive as a preprint, but we are also going to present it in the VTC 2023 Spring Conference next month in Florence. So if someone in the audience will be there, it will be my pleasure to discuss the dataset in person. So with this, I'm done with the explanation of the data set, and I want to now to tell you about the actual problem statement for ITU. So I'm just it's basically QoS prediction across environments, and for the next 2 slides, I'm going to focus on this across environments part of it. So I will recall this motivation I gave, that this idea that automotive communication is multi-environmental in practice and in essence. Which again, it means that the underlying data distributions across vehicles, operators, urban areas differs. Again, here you have these violin plots that we produced for the paper. So these IID assumptions that machine learning relies on are violated. So what does this translate to in practice? So for the challenge, we require that it's in the end it's just machine learning regression, but the train and test data split cannot be done in a random fashion. This is a very naive approach in this automotive setup, because you will never encounter this in real life. So there is a flexibility how to split the data between train and test sets, but it needs to be along predefined categories. So you take operator 1 for train and operator 2 for test, or you take different areas for train and testing, but random split is not allowed. So we also want to give a hint that depending on how you define your train and test split, it might be quite challenging to achieve a good accuracy. So there are certain techniques in the literature of domain adaptation or transfer learning to deal with this, and we encourage you to explore this and to see if this can push the envelope to get a good accuracy. Because again, this the normal machine learning setup has these assumptions that the source and target data have the same data distribution underneath, which it's not the case for our or like for automotive contexts quite often. So again, this would lead you into the direction of domain adaptation. So there's still some open questions to define the problem statement that we don't want to carve in stone, and we want to give you flexibility to explore different decisions and different problem setups, and so that in the end you just pick the one that you are more confident with, or you think it's more interesting. So I mean, from the introduction, I've already mentioned that QoS is not uniquely defined. So in our data, you could take data rate, delay, or jitter as a QoS parameter to predict. We recommend focusing on data rate, either in the uplink or in the downlink, because from this first analysis that we did in this correlation matrix, we can already see that delay and jitter, although it's not included here, it doesn't correlate very well with some LTE information from the physical layer. So I think it will, you will have a higher chances of success if you stick to data rate, again, either uplink or downlink. You can also choose many different input features, and again, the data has to be split along some predefined categories into train and test sets. Apart from this, you are free to pick any algorithm that you'd like, from machine learning from scikit-learn, or a fancy neural network using some deep learning library, and you can explore different methods for fine-tuning, from domain adaptation and transfer learning. if you think this is a lot of decisions to make, you can take a look at the reference example that we uploaded on GitHub, just to give you an idea what how to build your pipeline. In this case, we just decided to go with downlink data rate as the predictive quality of service parameter, and we are performing train and test split along operator. So we are training with operator 1 and testing with operator 2. But again, this is just a reference. You don't need to stick with this. We don't want you to stick with this. We want to see different flavors of multi-environment QoS prediction. So feel free to define a different PQoS problem with a different trained and test split. With the feature selection is also up to you. Although we will also evaluate that you don't just like put everything in the box, all the columns that are available in the preprocessed data frame, because in the end, this is not a good strategy. You want to be able to predict QoS with as few information as possible while retaining a good accuracy. So we will evaluate this, and I will explain more in a couple of slides. But yeah, other than this, you are free to experiment with all these different decisions or choices. Also, an important thing to add here is that it's completely okay to take this preprocessed data frame, cellular data frame.parquet. You can just download it and use it, plug in. But this might not be the best strategy, because the sampling interval is quite coarse, just 1 second. So maybe you want to upsample the GPS and data rate columns, and then you will have like a very with a data you will have a data set with a fine granularity that will maybe more powerful when training your algorithms. And also, we are not including all the possible information that we measure, because this would be too much data. But if you are confident with Mobile Insight, if you know where to find, in which Mobile Insight message to find which type of information, then be my guest to use that information in your algorithms. So now coming to the evaluation. So we are because we are not just focused on just like a very well-defined problem with with just like one metric. So we are going to evaluate you on the basis of 3 different scores that we are going to weight together. So the first one is the accuracy, and we have decided to take the coefficient of determination R2 as the accuracy metric. It's available in most common machine learning and deep learning libraries. It's very nice because the maximum is always 1, and the higher the score, the better the accuracy. So this also makes our life easy when it comes to evaluating. And you can use it from these libraries out of the box. We also want to evaluate the number of use features, which means that the less features you use, the higher score you will have. So we will calculate this score where we've just estimated that you won't use more than 84 features. So if you have 2 different algorithms with the same accuracy, and one uses half of the features as the other one, use or submit the algorithm that use fewer features, because this will mean a higher score for you. Also, because we are not defining every small detail of the problem statement, we will have a qualitative contribution depending on the choices that you made on the predicted quality of service parameter, how you are defining your train and test data sets, etc. So the submission will be over ITU's official challenge platform. And we require you to upload this, at least these three items. So these scores in a small CSV file. So you have a an example here from the reference implementation that's available on GitHub. So again, just like the reference to the team ID, which parameter you are taking at predicted quality of service, how are you defining train set and test set, and your R2 score and the number of used features. We also want you to upload the code so that we know exactly what you are doing, and a brief report, no more than 5 pages, explaining what you've done and why you picked these decisions about the problem statement. And if you fancy, you can also upload the model and the weights in a suitable format for replicability. So I'm coming to the end of my presentation. I just want you to remind you about the timeline that it was already mentioned at the beginning of the talk. So you can participate or register from now to end of August. Submission deadline is in September, and we will evaluate the solutions by the end of October. And afterwards there will be this evaluation phase until December. I hope the winning prize motivates you to participate. And I've come to the end of my presentation. I leave the references that I've used here if you want to take a look into it. And I only want to say thank you. I hope you have a lot of fun using the data, and I'm open to any questions that you may have. Thank you very much for listening.
Thank you so much, Rodrigo. Excellent problem statement. Thank you for working through the AI for Mobile Consortium and coming up with this. I would request the participants to raise the questions on the neural network or the channels that they are using. But maybe I can start with a few. So 4 vehicles. Why 4 vehicles? I think you're having platooning and maybe pairs of 2. But apart from that, I mean, what is the logic behind 4 vehicles? Why not say 2, or why not say 6 or something like that?
Yeah, thank you for the question. So, I mean, on the one hand, the number of vehicles, it was given by our resources. So, I mean, based on the people who performed the measurement, like it was us who did this drive test, and we were like all these different partners, BMW, Ericsson, Dresden. We just took cars and went out and performed measurements. So we managed to drive up to 4 cars, okay, on the one hand, for this platoon scenario where we were driving together, I don't think it would have been very challenging to drive with more cars than that. I mean, let's be honest, the more cars we have, the more information and the more complete the data set. But yeah, in the case of platoon driving, this would pose a safety issue in the public space. So we just like try to use, we thought that 4 cars was a good compromise. And in this platoon driving, this was an interesting use case from this first analysis of the project where we collected use cases and did a requirement analysis. And for this driving in 2 pairs, we also wanted to provide variety on the load of the cell. Maybe in this case we are using commercial networks, so maybe the difference between 4 and 2 vehicles, it's debatable whether it will have a big impact on the cell load or not, because you are also competing, or like you are also sharing your resources with all the other users in the network. But we were interested in this platooning use case, and for the pair driving, we also wanted to see about like we also wanted to have a scenario where we have that's more interesting from the correlation perspective. So if you have one car driving next to each other to another car with the same operator, the data from both vehicles is going to be highly correlated. But if you take the same both cars with the same operators and put them in different parts of the city, then it's the correlation will be completely different. So this is also the rationale why we took those measurements.
Interesting. Yeah. I think as you said in the beginning, the side link makes a difference. I mean, the platooning use case is basically for the side link information, right? But for this particular challenge or this particular problem statement, you are not focusing there. So I think that's probably the reason that you are explaining. If you think that way, it makes sense. I mean, the platooning use case and the number of vehicles and the challenges that you are mentioning. Yeah. Okay. Yeah, that makes sense. So this server. So yeah, your server is in HHI. What's the role played by this load on this server? Can you? I mean, did you baseline the server load? Is everything okay there? And what is the server? First of all, is the server common for all the profiles that you have, like throughput profile, delay profiles, and so on? Or do you have different servers for each profile? And in general, what was the health of the server? Is it lightly loaded? Did you face any problems at all with the server?
Yeah, that's actually a very good question. So it was the same server for all measurements, and yeah, it was just. I mean, I think it's part of our GPU infrastructure. If not, maybe there is some colleague in the audience that may correct me. But it had a good health because we also dimensioned our throughput profile in a way that we don't mess up. And we learned this the hard way because actually we were more ambitious on these throughput profiles for data rate measurements. So I don't have the figures in my head, but the original high throughput profile, I think it was two times or 4 times the one that we used in the end. So I think up to the target data rate, we set it up to 1 gigabit per second, which probably we didn't reach anyway. But what's the problem? That all these 4 cars communicating with the server over a commercial network at the same time. The firewall, or like the gateway, this was common to the whole research institute. So we basically did a DDoS attack on the first day of our measurements. So, and the IT had to call us and say, "Hey, what are you doing? We cannot work. You are taking all the bandwidth of the institute for your measurements." So we brought it down to some figure that was still demanding for the mobile network, but that was also respectful with our colleagues.
Really interesting. Yeah, thank you so much. And the CPU percentage, did you look at the CPU percentage or the network utilization? I mean, I think you already mentioned network utilization. CPU percentage was okay for the server?
No, not that I know, but I'm not aware of any issues on that front. I think the CPU was able to manage these 4 connections at the same time, as far as I know. Cool. So I don't think the CPU load was an issue.
Cool. Right. We have more time. Let me look at another factor. The other users in the network. So this is a commercial network. There are other users in the network. So they they would use up the resources also.
Mhm.
So actually, you already showed in slide 10. I think in slide 10 you had that physical layer parameters and RRC parameters and so on. Which are, yeah, exactly. So if you look at the TB size, transport block size, MCS, and RBs, these are dependent on how many users are competing for it as well, right?
Yes.
So what is the, in general, could you comment on what is the effect of other users in the network? I mean, we don't have, I'm guessing you don't have control over the number of users in the network, right? Probably you can select the time of day. I mean, if you maybe select the night, maybe there is less number of users. I don't know. So how do you, what is the effect of the other users in the network? Whether these are priority users, does time of day matters, and the geolocation. Yeah, geolocation matters as well, because there may be hotspots, there may be metro stations, subway stations, somewhere where there are a lot of people. So what is the effect of the other users in the network?
Yeah, you're right. The more users in the network, the worse your QoS will be. The less resources you may reserve for yourself. So of course, this has a negative effect, a negative impact on the quality of service. Unfortunately, this is something that it's not so easy to extract from the data, the cell load, because we were just using commercial networks, and we were basically, I mean, we just had some customary SIM cards, commercial SIM cards. So we weren't any kind of privileged users with privileged information. So we don't get the cell load from the base stations. We had other measurements where we were using a dedicated, or like a network infrastructure that where we had control over it. It was this 5G connected mobility testbed from Ericsson, where we did have access to such information as the cell load. And we've already explored this in some publications, and of course, this is a very valuable information to predict quality of service. In some, it might even be more valuable than signal quality in some scenarios. Unfortunately, because this is privileged infrastructure from a company with its own interests, we couldn't publish the data. But yeah, you are 100% right. Cell load and the number of users that you are that are in the same cell as you is crucial information. The best guess that you can make with this data set might be this traffic information. So you have this traffic jam factor. So the higher this factor is, the more congested the traffic is. So off of my head, this is the parameter that correlates the most with the number of users in the cell. But of course, this also only applies to automobile users.
I see. Okay, so it's a real traffic jam. Okay. Yeah, that makes sense. Yeah, thank you so much. Yeah, I think this is a crucial piece of information for the participants. Thank you so much. I think that I hope our participants are taking note of it. I think this is it's a very important piece. Yeah, I think otherwise, I think the problem statement is quite clear. Time of day. So you don't have time of day, I believe, no?
I don't have what? Sorry.
The time
of the day.
Yeah.
Yes, we do have. The data is actually indexed by it, so it's
timestamp. Oh, okay. All right. Yeah. Thank you. Yeah, that I believe that those two would actually cover what you mentioned, and right. Slide 18. Slide 18. Let's look at the scores. You mentioned 3 scores. How do you combine these 3 scores? So it's possible that I get a good first score, but I use up a lot of features, so I do badly in the second score. But Thomas does very well on the second score, and not so well on the first score. So how do you rate this combination of scores?
Yeah, so we are going to, it's going to be just a weighted average of the 3 factors. We are not so, we don't want to disclose how, like, the weighting of every subscore, because we don't want the participants to reverse engineer it and focus. So we want, it's an art how to motivate the participants to investigate all the things that we want to investigate by defining the score in a meaningful way. But we don't want the participants to just, like, reverse engineer the weighting score. So the only thing I can say is that they are ranked in by importance. So the R2 score is going to be weighted more than the number of used features, and the number of used features is going to be weighted more than the problem setup score, because this one is qualitative anyway. So it's important to give more weight to the first 2 scores, which are objective, I believe.
Very good. Very good. Thank you very much. The frequency band. You mentioned of the range 700 to 2700. That's a quite a high range. So does it mean that the route that the vehicles takes, the route of driving, in that there are different cells with these different frequency bands, and of course we don't know where is what cell. So it is possible that you might actually see different cells with these different frequency bands when you drive. So what is the effect of this huge range of frequency bands? Is it, I'm guessing that you might actually see this impact in the physical layer parameters that you are seeing, I'm guessing. But is there anything else that the participant should look at for this, as far as the frequency band is concerned?
Yeah, so I agree. I think if we focus only on the frequency band, the highest effect that this may have, like if we are compare 2 cells using 2 different frequency bands, is in the phi layer parameters, because the propagation characteristics will be different. But I think it's also, if we open up to other parameters from the cell, I think it will be very valuable for the participants to take a look at the bandwidth of the cells, because this also tells you, like, how much resources you can allocate. And so of course, if you have one cell with channels with a higher bandwidth, this is it's going to serve more like more data rate. I'm not the people with the person with the most knowledge about the LTE standard. So I may say some wrong things, but I mean, this is like just the rule of thumb things that come to my mind.
Okay. Yeah, I think that makes sense. Right. Yeah. I believe that that you're saying there are other features which makes more important. Right. I think that makes sense. I had something on the primary and the secondary cells which you had. I believe UE capabilities. Yes, that was my question. So UEs, the 4 UEs that you are using, they are all same capability. Like they are all capable of doing primary and secondary, and they are all capable of exactly same set of features. Is that right?
Yeah, they are all. They can all perform carrier aggregation with two different cells. So yeah, I mean, there was an artifact from Mobile Insight that the secondary cell was labeled as secondary cell 1 and 2, but we actually observed that doesn't matter. So if the devices are connected, I mean, have connection, so they are not in a tunnel, they will be connected to the P cell, the primary cell, and they might be also connected to a secondary cell, not more than that. And this is true for all 4 devices.
Cool. All right. Yeah. Thank you very much. That I believe we have everything that the participant needs. Abhishek is asking, maybe from the collected data, it is possible to do cell load estimation. Yeah, that's something which I was thinking too. Yeah, it may be possible. What do you think? What do you think, Rodrigo?
To do cell to so the question is if we can estimate cell load. So if one could use QoS or like if one could define the QoS parameter as cell load, is that the question?
No, can you correlate and maybe estimate the cell load from the collected data?
From which data?
The data which you have collected.
I mean, yeah, how? Like, maybe there is. I mean, again, I don't have a full knowledge of the LTE stack, so I don't know if there is some parameter in some Mobile Insight recorded in some message that provides some hints on this. I don't know if the base station provides this information to the user. I would say no. Like, why would they? But maybe I mean, I can only guess, but my answer would be no. But it's not a 100% no.
Okay. Yeah. Thanks a lot. Thanks a lot, Rodrigo. Patiently answering to all our questions. This is quite clear. Let's hand it back to Mia. Thank you.
Thank you.
Yes, thank you, Vishnu, for moderating the Q&A session, and thank you again, Rodrigo, for explaining today's problem statement. Again, all the information that you need you can find through the Slack channel by signing up for the AI for Good page, so please make sure to do that, and also keep interacting with us and other participants through all social media channels. Thank you, everyone, again for joining today's session, and have a good day.
Thank you.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
AI is a powerful tool.
This summit can help ensure that artificial intelligence charts a course that benefits humanity and bolsters our shared values.